So my name is Lito, and this is Botany with Bytes. So this talk has a lot of images, and to do that, it uses a Ruby gem called graphics, written by Ryan Davis, who's sitting in the back over there. It has axes in all of the right directions. It is absolutely my favorite graphics library I've used. It's still in beta, so gem install -- pre, and you can see a whole bunch of examples, very easy to use. All of my code is on GitHub, github/LitoNico, L-I-T-O-N-I-C-O. I am on Twitter as right down there. You can see it in the bottom of my slide. Tweet at me. I appreciate it. So imagine you are algae. Here's you, an alga. And we'll call you A for alga. And you're going to do what algae do, which is make more algae, in a process called mitosis. And so when you're done, you'll still be there, but you'll also have B, a baby algae. And so this process continues. Your baby will grow up, and you'll split off more. And algae, baby, alga. So this keeps going and going and going, and we're just going to start representing it with letters because it gets big. You know, A, B, A. Incidentally, for the same reason like breeding rabbits does, this will give you the length of each generation will be the Fibonacci sequence. So like 1, 2, 3, 5, 8. So this process was first described by a botanist named Aristed Lindenmayer. It's actually a human and not a plant. He called these, after himself, he called them L systems. They're very simple. They consist of a start, like an alga, and some rules, like one splits and a baby grows up. So let's talk about computers for a minute here. You may recognize this system as a rewriting system. We know those from like the game of life, if you've ever done that. That rewrites a grid based on some rules. The famous fractal, the Koch snowflake, that rewrites a line. This one rewrites a string. So since it's strings and since it's rewriting, this is a grammar. But what is a grammar, actually? The simplest and easiest definition of a grammar is what strings, or like grids or lines or things, can you make with rules, with any rules. The rules can be of the form, these cells get replaced in the game of life. They can be like the production rules of an L system. But for the purpose of this talk, I'm going to flip it around a little. And instead of saying what strings can you make, I'm going to give you something a little more familiar and say what strings can you match with these rules. And our favorite as programmers, our favorite example of this is regular expressions. Like, here's a regular expression. What strings does it match? I don't know. So when we organize grammars and when we talk about that, we can categorize them in terms of how much they can do. So regular expression, you need a special kind of a computer for regular expression, a finite automata. This computer right here is way more powerful than that. We don't even need to worry about that. So we'll draw this little square to describe all of the strings any regular expression can make. And if you're like me and have naively at one point tried to parse HTML with a regular expression, you know that it doesn't work. Like, so there must be more outside of that. Or actually, first, there are a subcategory of that called finite. We're just going to ignore. But outside of regular expressions, there are also context-free grammars, strings you can't match with just a finite automata. These ones need a stack. You need some kind of memory that you can append things to and get things off the top. And there are more beyond that. HTML is the most famous example of this. Context-sensitive grammars like C++, you need some random access memory to keep track of what's going on. Like, is it a function call or is it an instantiation of a class in C++? Beyond that, you have grammars called recursively enumerable that need possibly an infinite amount of memory. I'm not sure where Ruby lives on these. It's somewhere between the two of context-sensitive and recursively enumerable. Every time I open up parse.y to try to figure out, I'll read like 5 lines and just go, nope, and close it again. And of course, Perl is not parsable. That's not a joke. It's actually not parsable. Yeah. So my talk is about L systems. Where do they lie on this? L systems are a very strange slice of all of these. So an L system can match some finite grammars, some regular grammars, some context-free grammars, and some context-sensitive grammars. Still on? Yes, still on. Now, there are other L systems called IL systems that we're just not going to talk about. They're even stranger. So L systems are a strange slice of other grammars, and I want to give a concrete example because it's hard to actually think about these things. Like nested balanced parentheses. If you have an L system and you want to match an arbitrary number of parentheses, all just stacked up, all balanced, all perfectly nested, an L system can match the parentheses with a token in the middle that gives it a kind of seed to work off, like that initial algae. But it can't match just balanced parentheses. A context-free grammar can match both, and a regular expression, as you know, can't match either. So here's a quick implementation of an L system. You'll notice that it's dead simple. We're only going to be focusing on this actual logic part. The rest of it is just keeping track of the rules and the initial state. So here it is. You have a string. We're calling it the state. You split it up. You apply the rules with a dot map, and you join it back together. So an algae and a baby algae, split, rules applied, joined. You can throw this into a REPL, and it works just fine. And that gives us algae all in a line. But what I really want is more dimensions. So we're going to be talking about sprouts, like a little tiny tree that starts with a leaf, and each leaf branches off into a stem and a left leaf and a right leaf. And each stem just gets longer. But we haven't talked at all about a way to draw things in 2 dimensions, so I'm going to introduce first a very simple way of doing that called turtle graphics. Have you guys ever encountered this? It's the programming language Logo. Like maybe you've seen like in grade school how to program little spirograph drawings with this. I'll go over it if any of you don't know. You have a turtle that you have control over. You can program its mind and tell it to go forward. You can tell it to save where it is right now, the position and direction, and push that onto a stack. You can tell it to turn left and right by arbitrary angles and keep going. And you can recall previous states and use that to draw different diagrams. Now, we're going to be using the turtle to evaluate strings of symbols. So we need to tell the turtle what different things mean. Like, here's a new turtle. The string we're going to have it draw is S, left bracket, S. And I'm going to tell it S means go forward, L means go forward. We don't see that. Left bracket means turn left, right bracket means turn right, and push and pop. And so I'm just going to walk through how that works. So we're first going to go S. All right, turtle knows that means to go forward. Left bracket, turn left. S again, go forward. That's how this mechanism of drawing works. Now, there's no real reason for me to pick this kind of drawing other than I think it's really easy to explain. You could probably, like if there were some graphics programmer here thinking like, yeah, I could do that with rotation matrices and stuff like, you totally could. I just really like these simple mechanisms of drawing. So back to the sprout, and we need to tell the turtle exactly what it means to draw a left leaf and a right leaf. So at the end of a stem, we're going to save the current state of the turtle, the position and direction, turn left, draw a leaf, and then restore, so back to the tip of the stem, turn right, and draw another leaf. And that'll be sufficient to get us drawing in 2 dimensions here. We'll set up our sprout and our turtles. We have the L system we just talked about, and we're telling the turtle what each of those symbols mean. And we'll draw the thing. So the first generation is just L, right? Just a leaf. It's boring. We don't need to worry about that. Second generation, equally boring. We're not going to talk about it. It's what we saw at the beginning. But the next generation is interesting. And I'm going to walk you through it just to make sure we know how the turtle is drawing this string up at the top. So here's some stems. We'll save the current position. Turn left, draw another stem. Save the position there. Turn left and draw a leaf, and so on. I think you guys get the idea, right? So trees don't actually look like this. At least that's what I used to say, because there is a plant. It's called a Drosera binata, which really does look like that. It's a drawing because there are no public domain images of the thing on the internet, but it really looks like that. It's got that branching structure. It's a carnivorous plant, but like most ordinary trees, they don't look like this. So let's do an example of something that better matches reality. Here's a juniper branch. Hard to tell what it looks like just from the grammar. But what this says is you start with a twig, and each twig goes into this shape. And as you run that, here's the thing evaluating. You'll wind up with something like this. Now, this isn't a perfect match of what a juniper branch looks like, but it's pretty close. I haven't factored in things like the buds at the end or the different length of the twigs as growth happens, but this is very close to the actual mechanism the tree uses. So we've talked about earlier in the section about grammars that you need a computer to be evaluating these things, and you have the plants creating these structures. So plants are computing as they grow, and I think that's super neato. You can also do weirder stuff unrelated to plants with these L systems. Draw Sierpinski's triangle and little squiggles, like all sorts of stuff. There'd be dragons. So let's take a different view of a stem. This time we're going to be taking a cross section through the tip of the stem as it grows. So looking top down, you can kind of see taking the plane, bisecting it. And so this is the, viewing the plant from the very top. And that stem, the meristem, where new leaves bud from, is filled with plant growth hormone. So as a new leaf buds from the center, it sucks up from the surrounding area all of the growth hormone and then sets off in search of more. Well, the next leaf buds and has to go off in a different direction because it can't follow the first. There's not enough growth hormone left, and so on and so on and so on. Now, if we were going to simulate this for real, like the time complexity would be awful. I'm kind of using this as a proxy for how awful the code would be too. Like, gonna have to keep track of some kind of fluids in there. I don't want to do that. So we're going to build a simpler model. Now at Cambridge, the first time this mechanism was described, before people even knew about the existence of growth hormone, scientists described a charged particle model of leaf growth, where each particle repels against the surrounding ones, which gives the same effect as each leaf searching for more growth hormone away from its neighbors. And you can do this in a real experiment, like on a plate with little drops of ferrous fluid. And they'll form spirals much like real leaves do. I'd like to take a minute to appreciate just how steampunk this model is. We've got plant hormone represented as electricity and electric charge. We've got little drops of iron fluid as leaves. And so I can code up a simulation of this as well, where we're just dropping in little particles, and they each repel according to the laws of electricity. And so you'll notice, as the simulation goes on, they start by repelling immediately. But as it keeps running, they'll start to repel at an angle based on the sum of the charge from all the neighboring particles. The time complexity and the awfulness of code is roughly O of n squared. Not going to worry about optimizations on that one. By the way, this was Alan Turing's work. He called it the hypothesis of general phyllotaxis. He was the first person to describe this mechanism in plants at all. So I think the intersection of plants and computers goes back all the way. Turing, the inventor of the computer, essentially, was the first person to describe this process. He later refined it to even deeper understanding of the biology of how plants work. So this is what Turing drew in his notebook. This is the actual image. And we can notice, just like Turing did, that each leaf sets off at a particular angle from the next one, and it's always the same angle. Now, Turing derived this from a closed form solution, like he actually calculated the math. We can just measure it, and it's about 137.5. So there's the closed form. I don't know how we got it, but there it is. And so now that we know that angle, we can use an L system to simulate this structure of growing plants. We can just say, all right, we're going to rotate the stem 137.5 degrees at each step. And, boom, artichokes. Works. So the time complexity is fine. We only need to run the L system once. Like we saw the code, there's not much more than about 20 lines to do this. Much better in all around. Let's go back to algae in 3 dimensions this time. Here's you again. And this time, in a line, all of your neighbors, we're going to have each alga divide down. And we're not going to worry about the baby or the full-sized ones. It's just going to be each splits down the slides, as it were. Boom. Except life is complicated, so some of them split more than once. But it's all right. And this is going to keep happening. So to keep talking about this, it's a little hard to draw more and more and more of these guys. So we're going to simplify this dramatically, also make it easier to code. These aren't actually getting smaller. I'm just running out of space to draw them because there are more and more, right? So to represent cells, when a cell grows, it'll grow until it pushes up against all of its neighbors and form this kind of crystalline pattern. But to keep track of that, that's a lot of edges and a lot of vertices to keep track of. So we're going to swap it around. Instead of keeping track of the edges of each cell, we're just going to keep track of the centers and which neighbors it connects to. This is called taking the dual of a graph, if any of you guys have encountered that idea. But we'll just connect the center of each cell to each of its neighbors. Like, you have these guys. So now here's the drawing. Each cell is the dot, and each edge is its neighbor. It's the same graph. You can extract one from the other. It's just flipping it around. So as these grow, each of the alga is the same size. Each of the connections stays the same distance away, so let's simulate it. Oh yeah, here it is without the cells themselves. There it goes. That's what happens when each of the cells stays a constant distance from all of its neighbors. There are more and more and more as you go down the screen, so it gets rufflier and rufflier as each one pushes away. And this pattern shows up in all kinds of plants. Like if you walk outside, you'll see some euphorbia that demonstrate this pattern. I'm from the Pacific Northwest, so I see it a lot in things like Oregon grape or holly plants, any of those guys. So I want to talk a little bit about this as a kind of surface that happens by the way plants grow. When we talk about flat surfaces, they're not curved at all. They're, you can just walk across this floor and not worry about it bending or anything. If you have something like a sphere, we call that positive curvature, because as you walk, you're getting closer to any other point. You're curving back towards the surface. The opposite of that, the sphere, is what I've just described, which is this kind of bendy saddle shape that mathematicians have called hyperbolic and given it the name of negative curvature, it being opposite the sphere. You can also talk about different properties. Oh yeah, that's the one plants have. You can talk about different properties, like how many sets of unique parallel lines. Each thing has, like the first one has one set, the hyperbolic space has lots. The point I'm trying to make is that plants don't care about the mathematical properties of this. They're just doing it. They're doing it by cell division. And you can actually verify this. Like, I guarantee you, if you go up to an Oregon grape and say, like, man, what beautiful hyperbolic leaves you have. Like, can you tell me about how you generated those, like the distance between each point? I guarantee you it will not answer. Thank you. That's all I got. Hire me, please. I'm looking for jobs in Seattle, Washington, or remote if you're really awesome. So come talk to me. Questions? The question is, what does the gem do? It's a way to draw things on the screen. It is not my gem. It's written by Ryan. Can you wave your hand up there? Yep. You might mention it in your talk later. Maybe. Maybe. It is similar to processing. All in Ruby. It's an interface to SDL, which is the simple direct layer for drawing things on the screen. And you can plot points, you can draw lines, you can draw circles, any basic shape. You can use Ruby's matrix library to do 3D math if you want, and draw things in 3 dimensions. It's very simple. It's geared towards simulation code rather than game code. So I was really frustrated with Gosu, the Ruby game library. So if you have also tried to draw stuff on screen, you wanted to write in Ruby rather than processing strange kind of Java, give Ryan's library a try. More questions? All right. That's it. Thank you.